This is the gearbox of my new lathe, which normally of course is situated right here, but now it's lying here on my bench. I took it apart because two of the gears has serious damage. So project for today, making new gears. This gear assembly is one part, which could make it maybe a little bit difficult. And the other one I have to fix is also one part. Normally these two gears, depending on how we set it, these two are engaging in each other. And when I change settings on my lathe, this same gear also fits in here sometimes. Now lucky I have here an also 32 gear, and it also fits perfectly in here, which means these gears I checked is the same module as for my old lathe here, 1.5. And even more lucky I have a gear cutter for it, now already fixed on an arm, but I have the right cutter. And I have what I think material. This here is more or less the situation. We have of course the gear, that is one part with the shaft and then this sliding thing in here. My idea is to cut off a piece, make a shoulder like this, and then out of my way too big part over there make a ring like this, and here we have the bore of course and the teeth, more or less like this. When this ring is finished I can press it on this part that is cut out and then install, for example, 2 or 3 cute little screws to hold it all together. My first idea was to first cut off the teeth and then install it here in the welding rotator and build up new material. But I don't want to do this because I'm a bit afraid that with the heat the thing will have some distortion and doesn't work anymore. So the ring, it will be. Let's go for it. I made here a little arbor, and of course it didn't clean up completely, there's still a piece of keyway in here, but for the moment no problem. On this arbor I can fit this one in theory. Indeed, it fits. When I file it, it feels more or less hard. But I think I will be able to cut it. First center drill and then cool. Yeah, that could work. My first idea was to cut off this ring here in the lathe using my rear tool post. But I think this is way too much stick out, so this is an ideal recipe for disaster. So I will cut it off in the bandsaw. Alright. I had to rotate my part a few times because the blade guide here is completely aft and still it's touching the jaws here. Yes. The countersink for these two little screws here I will do after. Because to do this I have to take out this bolt. But if I do, I lose the center. So first I will cut the teeth. So let's install the thing here. To cut my little gear here, I need to bring up the old Zwik at least 30mm more. But this support arm is gonna touch this support arm. That's not gonna work. So let's find another setup. I took off the support arm and installed another arbor. And I already took one cut just to be sure that it works. And everything seems just fine. Cutting speed about 20 meters a minute. And a feet of really not much. I have a gear. Let's take it out of here and see what we've got. I think it's good work. And in this one, it fits. So I think that's a really good result. Let's make another one. This one. To make this bigger gear, I would like to use, of course, more or less the same system. Cut off these teeth and then make a ring, press it on and good to go. But as always, there is of course a problem. With the plates I have for this dividing head, I cannot make 48 divisions. So once again, the shaper to the rescue. Because on the shaper you can make whatever you want. And if you don't have one, you're on your own. But this will be for next week's video, because now it's time for inland barging part 2. In part 1 I explained a little bit how we can find our way on the water. Of course on the road it's very easy because you have lines and you have to stay between the lines and there are signs and signals everywhere, no problem. On the water is of course a little bit another story. And a good question could be of course, okay, all this theory, but how does it look like in real life? Well, like this, for example. This time we will talk a little bit more about, for example, cargo and cargo operations. My first job in inland barging was on a towboat, you know, the kind of push boat that pushes these barges without engines. And we transported coal and iron ore for the steel industry. The idea is of course very simple. We have a kind of shoebox, that's all. And in here we're gonna load the coal or whatever, or sand for example. And these shoe boxes, we push them around with a towboat. Looks more or less like this, for example. The great advantage of this system is you load the barge, you bring it where it has to be, and you can leave it over there. Take another barge with the same push boat, of course, and you can switch barges. Very handy. Now, in this shoebox we put 2,000 metric tons of cargo, and the depth, total depth, is somewhere, if here is the water, yeah, we have between 3 meters, little m of course, and 3.5 meters depth in the canal. A fully loaded barge, we could push it at a speed of 10 kilometers hour. And now you're gonna say, what, only 10 kilometers an hour? That's not much. I absolutely disagree. I think this is very fast. Let me explain. Most of the time, the distance we had to cover between the loading point and the discharge point, the client of course, was about a 3-hour sail. So loading point, this loading point, 3 hours. We load in total 2,000 tons, which is the equivalent of more or less 200 trucks. Now, loading 200 trucks in 2.5 hours and then bring them to the other point, I don't think that's gonna work. Especially if you think about it, between loading and discharging point is a city. In 3 hours, bringing 200 trucks through the city and the other side of the city, that's not gonna work. And we do it in a barge in one time. And the second advantage is, of course, for 200 trucks you need 200 engines. And we transported these 2,000 metric tons with only one engine. Same as a truck engine, same more or less 400 something horsepower. So I think that's a win. And after 2.5 years of working on towboats, then came the global crisis of 2008. And the steel industry closed its doors, and the cement and all these other industries stopped working. So almost everyone in the company where I was working lost his job too. No work anymore. But I was able to survive doing little jobs left and right, you know, working on a small boat with a crane, pontoon thing. And I also worked several times on a passenger ship, tourist boat. Now that was not really my thing. I have absolutely no problem with people, but all these passengers on this ship, they've all seen the movie Titanic. So they're all specialists in boating and navigation, and they came to tell me how I had to do my job. So, not my thing. And then finally I could find a job in the bunkering. Now, what is bunkering? If you drive your car and you need to fill it up, you go to the gas station and fill it up. A sea vessel like this one has of course a little bit difficulties to go to the gas station. So we have a ship that is a mobile gas station, and we deliver the fuel to the ship. That's what it's all about. But before we do the fuel delivery, it's maybe a good idea to go first to the refinery to fill up our barge. I have taken only one secret picture of this loading arm, because normally we are not allowed to take pictures on refineries. And this is more or less how it works. On the barge I used to work before, this Charles D barge, we could load maximum 1,200 metric tons of cargo. And in the tanks we had a free space, total free space of a little bit more than 1,400 cubic meters. So before we start loading, of course we have to calculate to see that indeed if we order, for example, 1,200 tons, if indeed we have enough free space to put it all in, because of density of the product. If it's water, the density is 1. Of course the weight and the volume will be the same, but the diesel we loaded has a density of between 0.85 and 0.89, and depending also on temperature, of course it dilates or contracts. And after all these calculations, and we see that indeed we can take all the cargo we ordered. Of course there's also tons of paperwork and safety procedures and all this shit, you know, too much. And then we can start loading, and the diesel will go in 12 separate tanks. Now here there are 6, but of course it's 6 both sides of the ship, yeah, left and right. And then we do this in both tanks at the same time to keep the ship level. If, for example, we start loading in tank 3, 1, 2, 3, 3 left and right, and before the diesel reaches the maximum height, the ship will break in two and sink. That is of course not what we want to happen. So we start loading in all of the tanks at the same time, and the level goes up more or less at the same time. Now an empty ship is always leaning backwards because of the weight of the engine. So diesel we first fill up these corners, and then slowly but surely the ship will level out. And the maximum height we can load is 98%. If we fill up 100%, and with the sunshine, for example, the temperature of the product inside will rise, of course it's gonna flow over. Diesel in the canal, it's not a good idea. Too much paperwork. On my little sketch here I also drawed 2 very small tanks, one here in the front and one in the back. These are tanks, but not really cargo tanks. We call them kofferdams. In case, for example, of fire, because here in the front is an engine room, risk of fire. At the back is also engine room, also risk of fire. Now fire and diesel, it could be dangerous. So what we can do in case of fire is fill up the kofferdams with water. And this will separate the cargo from the fire. Of course, during this transfer of diesel into the tanks, there has to be always someone on deck to monitor the level in each tank, to keep the ship in balance. Because in the beginning all the diesel will go to the tank number 6. and nothing in one. So we have to play with valves and all this, and of course also prevent it from overflow. There is an automatic alarm system, of course, on deck that prevents from overflow, but just like every other system, it could fail. Now, we never had a fail, but it can happen. Yeah? For example, during the winter time, when it's freezing cold and everything on board is frozen, and the diesel they are pumping in is somewhere 40 degrees Celsius, maybe 45 degrees Celsius. That's nice, because we can warm our hands and feet on these pipes. So even in winter, nice job. But not when it rains. When the transfer is finished, of course we have to check if the quantity is correct. Now on a tank ship it's not too complicated, because all we have to do is measure the height between the level and the bottom of the barge, and all these tanks are calibrated. We have a certificate that tells it this tank number, I don't know, has a volume of, so all we have to do is calculate the total volume we have on board, and from that number we can calculate the weight. Of course, for cargo ships with a dry load like sand and coal and all these other things, the sounding is a little bit different. This is our ship, and the cargo inside, well, that's all we know. How can we calculate how many tons we have loaded? On every ship there are marks, white line, one here, one in the middle, one somewhere aft. The distance between this mark and the bottom plate of the ship is known, because we have in the book of the ship, we have all these numbers in tables. Yeah? So all we have to do is to measure the level of the water. Now of course here's a bit too much wave, so it's not really easy, but we measure between this mark and the level of the water. If we have this number 6 times, we take an average, so we know this average number. It's very easy to calculate this part between bottom and level. And then in our table book we can see if the ship sinks in, for example, for 2 meters, we know we have 800 tons. Just a number example. I found online, because I have also some pictures online from the last barge I used to work on. And this one is where it's empty, and this one is fully loaded. And this barge, fully loaded, contains 1,400 metric tons of diesel. Now imagine I can bring home all this diesel to use in my heating system. I can heat my house for about 800 years. 800.